So this is a relatively short slide. The p-value is used to compare with, and this is called alpha, also known as your significance level. So when you look for significance level, that's right here, alpha. Okay. So to make your decision, you have to have a significance level chosen. That significance level is given in the problem. It'll say things like significance level is 10% or 1%. It might say the probability of making a type 2 error is 2% or 5%, or it might not say anything at all. And if it doesn't say anything about significance level, you're to assume it's 5%. So if you don't see it anywhere, assume 5%. And that's the same in real practice as well. The general understanding is that 5% is the amount of error you're willing to allow. So in just a minute, we'll talk a little more about significance level, but for now, step 4 is your decision rule. If p-value is less than or equal to alpha, you will reject. Okay? If p-value is greater than alpha, you do not reject. All right, keep that rule nearby. Maybe write it down somewhere with your key information. That is the rule that will be followed for all tests. Okay, and not just in this class. This is the rule that we constantly use. Everybody uses it for every test. It's the same rule, same amount, same conclusion. Again, this is a universal thing. So keep that nearby. That is how we make our decisions, and it won't change. All right, so let's give you a little more information about significance level. So significance level is alpha. What it is it's the probability of essentially making a mistake. Okay? It's the chances that you're going to say, let's go back to the example of 20 being our average and 18 being our sample average. If you get 20 as the assumed information, but then you go ahead and do an experiment and you get data that indicates 18 is the average. And then you say, okay, I believe the average is not 20, but is in fact lower and closer to 18. Alpha, the significance level, is the chances that you are wrong. Okay? So it's the chances that you say, you know what, no, I don't think the assumed information is right. I think it's lower or greater than that. The chances that you are wrong and it's actually just a random chance you got that lower or higher number, that's the alpha. Okay? So that's why you're going to see alpha is usually things like 1%, 10%, 5%. Okay? We want to make sure that our chances of being wrong are very small. It makes sense that we wouldn't want to change the assumption unless it was we were getting information very, very out of the ordinary. It should be hard to change the status quo. I mean, there's a reason that the average is assumed to be a certain number. You would assume it's based on prior testing, prior information, an assumed level, assumed information over several years. So it should be hard to change the assumption. And that's what we want it to be. We want it to be hard to change the assumption because, I mean, it's assumed for a reason, right? So the chances that you say that the assumption is not true and then are wrong should be low. Okay, it should be low. If you're making the decision the assumption is wrong, you must have really good evidence to back it up. So the chances that you make that statement that the assumption is incorrect, but you're wrong, should be very small. And that's what you're going to see, that the alpha is only 1 or 5 or 10%. We're not willing to give you a lot of room for the error. So typically, you, the researcher, must decide on the level of significance before formulating the rule. So level of significance should always be decided before you do the test, not after. Like I said, it's typical for 5. That's usually what you just go based on. The other thing that we do is the level of significance is typically chosen based on the consequences of the incorrect decision. Okay? So as I mentioned, alpha is all about you making the rejection of the assumption when in fact the assumption was right all along. So you made the mistake. well, there can be consequences to that mistake, and depending on how severe those consequences are, we take that into account when we're choosing our level of significance. So sometimes you might also call the level of significance level of risk or probability of a type 1 error. Okay? The reason it's a type 1 error is because there's two types of error, type 1 and type 2. Type 1 is alpha, type 2 is beta. We don't really do anything with beta. We then take our significance level and we compare it with alpha, which you saw on the previous slide, and that's where we actually finally make the decision whether our results are statistically significant or not. Once we have that decision of, yes, you know what, my p-value, my chances of getting my numbers are super, super small, less than the significance level. If you say there's a, you don't want to risk more than 5% chance that I'm wrong, well, it looks like my information is telling me there's only a 1% chance I'm wrong. So since based on my sample information, there's only 1% chance I'm wrong, and you're willing to accept 5%, then we reject. Okay. All about your, your chances of being wrong. It's kind of a big part of it. You're examining what would happen if I change the status quo. What are the chances that I could be wrong? And if your chances are extremely low, lower than you're willing to, lower than the acceptance, 5% or 1% or 10%, then you're willing to go with your information. So I mentioned a minute ago, errors. It is important that people who are performing statistical tests understand the error that is possible. And it's important to understand that when you do these tests, they are statistical tests. They are not any kind of, there's no guarantee. No matter what, there is always a chance you have made a mistake. Okay. The unfortunate part is you will never know if these mistakes could have been made. There will be no way to know. Unfortunately, unless a whole bunch of really bad things start happening as a consequence of your decision, you're really not going to know whether or not your conclusions are correct. There's no way to avoid that. There's two types of errors that you could potentially make. Type 1, type 2. Okay? Type 1 is you decide, so again, let's go with the example of 20 as the assumed average, 18 as our sample. So you decide that the average isn't 20. Okay? You decide the average isn't 20. All right. You believe it's 18. Okay? If that's true, you're fine. Okay? You've made the correct solution. You've made the correct decision. However, if you decide, no, the average is not 20, I think it's 18, but you're wrong and H0 is true, you've made a type 1 error. Okay? The other side of that is you might say, all right, I got my information, you think the mean is 20, I have no reason to doubt. Okay? So based on what I've got, the assumed average is that it's 20. I don't have any evidence to back up that it's not. So you come to the conclusion that, there's no change, the assumed average is correct, and if it is, if H0 is true, then you again have made the correct conclusion. You've decided not to reject H0, you are sticking with the assumption, and the assumption is true. But if you decided that, yes, the average is 20, but in fact it wasn't all along, you've made an error, a type 2 error. Okay? Again, there is no way to know whether you've made these errors or not. Okay? All we can do is determine the chances that we make these errors, and we try to avoid them as much as possible. And some may say, well, why not just make the probability of these errors, as tiny as possible, 0.1% or something like that. Unfortunately, what happens is if you increase the chances of a type 1 error, you decrease the chances of a type 2, and vice versa. So if you increase the chances of one error, you decrease the other. Or if you decrease the error of one, you increase the other. So it's a balancing act, right? Sometimes what statisticians will do is they'll look at the consequences of each error and decide whether they might be able to lower the risk in one area at the expense of increasing it in another. So to give you an example of something like that, so again, if you were in class on Friday, you already heard this. You can skip over this. But for anyone that wasn't, I want you to think of these two scenarios. H naught is the assumed, right? Now, when people go skydiving, before they go, their parachute and their equipment has to undergo strict testing. So what happens in that testing is that a person will assume that the parachute is defective until it goes through rigorous testing and gets through a whole bunch of checklists of, is this good? Is this working? Is that there? Until that point, a parachute is defective. It's no good. It's not ready to be used. Not until it's gone through a whole bunch of testing, right? So once it's gone through its testing, the parachute becomes good, right? And those become our two hypotheses. Now, if those are the two outcomes of testing, either the parachute remains defective, that's the assumption, it goes through testing, and either we learn it's still defective and no good, or now it's cleared, and it's good. There's two types of errors that could happen. And I think you're going to see why some people choose to make one error small at the expense of the other. So these are your two scenarios that could happen. A type 1 error. If you do a type 1 error, it means you reject H naught when in fact it's true. So what that means in our example is I reject this. Okay? I reject H naught. I think the parachute is good. Okay? I think the parachute is good, but I was wrong. It's defective. Okay? Either I think the parachute is good, and I'm wrong, and it was in fact defective, but because I thought it was good, I jumped out of the plane with a bad parachute. Or, type 2 error, I don't reject H naught when in fact it's true. So if I don't reject H naught, and I say, okay, I don't reject H naught, I do think it's defective. I see no evidence to say it's not defective, so I believe it is, where in fact it was a good parachute, but because I thought it was defective, I didn't jump. Which one would you rather make? Which error would you rather have happen? Would you rather think the parachute is defective, even though it's good, but you don't jump because you think it's defective? Or would you rather be the person that thinks they have a good parachute when it's defective and you jump out of the plane? Well, obviously, we would rather be in the type 2 error category. Okay? This is the one that's going to, it's going to waste a few extra parachutes, but it's not going to cost anyone their life. So if someone was trying to conduct testing with this in the 2 errors, they would likely say, you know what, we need to reduce type 1 error as much as we can. We need to do extra testing. We need to have extra checkpoints. We need to make sure that this type 1 error doesn't happen. Even if it means by reducing type 1, we increase type 2, well, big deal. If it means that we lose a few good parachutes by accident, and it costs a few $100s to, to get rid of some that we didn't actually need to get rid of, so be it. It's a lot better than having people jump out of a plane with, good parachutes, with parachutes they think are good when they're not. So that's sometimes the idea of what reducing your errors can be. When it comes to choosing your alpha, you want to reduce your alpha as much as you can if the consequences of making a mistake are really bad, then you know what? Yeah, let's reduce the error as much as possible. But if the chances of making a type 2 error are really bad, you might be willing to say, okay, well, let's increase alpha a little bit to maybe 10% in order to make sure the type 2 error isn't as bad. So it's a matter of a balance act. And if the consequences of neither are very dire, then we don't worry about it too much and we just use 5%. Okay? But certainly if the consequences of one error or the other are really, really bad, you might want to consider lowering or increasing the alpha depending on which error is going to yield the worst consequence. Okay. All right, conclusions. All right, when it comes to conclusions, you have certainly some leeway. You can turn your conclusions, into a nice conclusion sentence, however you'd like. However, I strongly recommend using this type of wording because you have to be really careful how you word a conclusion. So I'm going to show you. If you reject H naught, what you're saying, and you'll know if you reject or not based on that step 4. If you reject H naught, it means you have evidence to support H1. Okay? That's pretty much all you can say, is you have evidence to support whatever's in H1. So if you say in H1 that you think the mean is less than 20, then you can say, therefore, there's enough evidence to say the average, whatever, is less than 20. But that's it. Okay? So what this means is that we choose H1. However, what you need to understand, it's very important, you have not proved anything. Okay? You have not proved anything. You cannot be 100% sure you didn't make an error. That's the whole point of the previous slides that we talked about with error. So you have to be careful on how you're communicating your decision. You can't be too definitive. There is always room for error in statistics. So the best we can say is based on our data, with support of our evidence, this is our conclusion. Okay, you can't say I now know for sure that the mean is not this, or that I've proved that this isn't true. You haven't proved anything. All you've done is use your evidence to make a decision. Okay. Same goes the other way. If you decide to not reject, you don't have evidence to support H1. I used to keep them straight with just the nots and the nots. So a not reject does not have evidence to support H1. Okay? But again, remember, you're not actually proving anything. You can't prove anything. Okay? It's not possible to, again, a proof requires, to be 100% sure I can prove beyond any all reasonable doubt that this is true. You haven't proved. Okay, you've simply done something based on evidence. All right, so to complete a hypothesis test, make sure you conclude with a proper sentence and make sure it has units and relates back to your problem. So don't use words, try to think of it as giving a conclusion in layman's terms. Don't use any statistical terminology. Try to just use the words that were in the question. So something like, my data supports that the average is less than $20. Okay, someone is going to understand that. Whereas if you start using words like, hypothesis, null hypothesis, reject, do not reject, in conclusion sentences, it's not going to be well understood. Okay.